Hello and welcome to another Crafting Interpreters video. In this series, we are going to read the book Crafting Interpreters by Robert Nystrom. This book is available for free in its entirety on the website craftinginterpreters.com. And we are going to be implementing the interpreter, which was originally written in Java using the Go programming language. And since I've gotten some very nice feedback on the initial videos, I'm going to try and make more videos like these. And in the previous video, we implemented the majority of the scanner. Our scanner currently supports several tokens, including all the single character tokens, like these parentheses, or bang equals, or equals equals, and so on. We also support comments and string literals and number literals. And one thing I wanted to do is I wanted to modify the scanner so that it reports errors to the interpreter using error objects rather than strings. And to this end, I'm going to implement some new error types. So as we can currently see, the report error function is currently uses strings as a second argument. So I'm going to modify it to use error, like so. And then the report function okay, this is a string as well, and then this is the error, and this is the error, like so. So I think we can define all of the errors in a separate file called errors.go. This is also in the main package. And what errors did we find until now? So in the scanner, okay, we have an error called unterminated string. So I'm going to call it error unterminated string. And that's just going to be a simple error literal like this. And you know what, we probably could include the line number in the type as well, but for now I'm just going to use a simple I'm going to make this one as simple as possible. And this is going to be error unterminated string. Okay. Oh, and also apparently it is possible to pass a string to a string. A string also seems to support the error interface, which is I guess good. Okay, no, it doesn't. So another one, yes, this invalid number literal. Errors new. Okay, and error invalid number literal, like so. Do we have any more errors? Okay, unexpected character. Where is it? It's here. Okay, does this compile now? What does, okay, yes, so we are getting the unexpected character thing. Okay. And Yeah, okay, this is fine. Also, what were the other to-dos I wanted to do? 1.103. I think we can remove this. And report the parsing error if it occurs. Yeah. These are not to-dos anymore because we have handled these. And yep, this works just fine. Okay, so what we just did is we replaced the initial implementation of report error with an implementation that uses error interface, it uses actual Go errors. And the reason we did this is this way we can actually implement these as structs rather than just simple strings, and this way we can add some additional data and we can use some custom formatting. And in general, it's just much more powerful. And I guess this is a good moment to commit. Okay. So I'm going to go ahead and continue reading the book because it seems like a lot of my viewers actually enjoy listening to me reading the book. And the last thing we did in the previous video was implement scanning numbers. So the next thing we are going to do is we're going to we're going to implement reserved words and identifiers, which is section 4.7. Reading the book. Our scanner is almost done. The only remaining pieces of the lexical grammar to implement are identifiers and their close cousins, the reserved words. You might think we could match keywords like or in the same way we handle multiple character operators like less than or equal to. For example, if we encounter like this, if we encounter O, we match on R, and so on. Consider what would happen if a user named a variable orchid. The scanner would see the first two letters, or, and immediately emit an or keyword token. This gets us to an important principle called maximal match. When two lexical grammar rules can both match a chunk of code that the scanner is looking at, whichever one matches the most characters wins. Side note, consider this nasty bit of C code. -,--a, semicolon. Is it valid? That depends on how the scanner splits the lexemes. What if the scanner sees it like this? -,--a, semicolon? Then it could be parsed. But that would require the scanner to know about the grammatical structure of the surrounding code, which entangles things more than we want. Instead, the maximal match rule says that it is always scanned like -,--a. It scans it that way, even though doing so leads to a syntax error later in the parser. Back to the text. That rule states that if we can match orchid as an identifier and or as a keyword, then the former wins. This is also why we tacitly assumed previously that less than or equal to should be scanned as a single less than or equal to token and not less than followed by equals. Maximal match means we can't easily detect a reserved word until we've reached the end of what might instead be an identifier. After all, a reserved word is an identifier, it's just one that has been claimed by the language for its own use. That's where the term reserved word comes from. So we begin by assuming any lexeme starting with a letter or underscore is an identifier. Okay, I'm going to do a split screen, and this is probably going to completely screw up the layout. And in this switch in the scanner, which I think is here, else if is alpha C as identifier. I'm also going to call it a scan identifier. Okay. The rest of the code lives over here. Private void scan. Where is scan token? Func as scanner scan identifier for is alpha numeric as peak as advance as add token token type identifier. Okay, and then we had this is digit thing, is digit helper. So I think we can add the following helpers after is digit. Func is alpha C run bool return C is greater than or equal to A and C is less than or equal to Z. By the way, we do not need those parentheses, at least in Go, because the end operator has is binds stronger than OR. So this should be interpreted correctly anyway. Greater than or equal to A and C is less than or equal to Z, or C equals an underscore, like this. Maybe we could. Okay, can we split it here? Yes, we can. Okay, great. And then func is alpha numeric crun return is alpha C or is digit C. Okay. Does it work now? Yes, so now we can correctly scan identifiers. So as the book says, that gets identifiers working. To handle keywords, we see if the identifier's lexeme is one of the reserved words. If so, we use a token type specific to that keyword. We define the set of reserved words in a map. And they say this goes in the scanner. So I guess we could, I think I'm going to put it in token type. Var keywords. And this is going to be a map of string to token type. And that's going to, like so. So end equals token type end. Class is going to equal token type class. Oh yeah, and this is going to be a lot of typing, so I'm going to do some vim magic. So I'm going to remove everything up until the parentheses. So norm df left brace, and I'm going to remove the right parentheses, and I'm going to replace the comma with a colon, and then I'm going to add a comma at the end, and then I'm going to make all of these constants Pascal case. So I'm using a NeoVim plugin. I think I don't remember what it is called, but it basically replaces, it basically modifies casing, so it can convert between snake case and camel case and Pascal case and so on. And then I need to go to the last word and insert token type, like so. Okay, great. So then after we scan an identifier, we check to see if it matches anything in the map. Okay, so where was this? In scan identifier. Okay. Text equals s source s start up to s current, and we convert this to a string, and if t ok equals keywords text and there is something in the map, then we add token t and return. Otherwise we add an identifier. So let's see, go run, return identifier. No, this is incorrect. Okay, yeah, this should match if this is okay. Okay, return test. Okay, so now it correctly matches the returned keyword, and it correctly matches the test as an identifier and the semicolon as a semicolon. So what if we say and or test class function? Yeah, okay, this all seems legit. Back to the text. If so, we use that keyword's token type. Otherwise, it's a regular user-defined identifier. And by the way, I forgot to mention, the whole source code of the program we are going to write is going to be on GitHub, and there is a link to the source code in the description below. So, and also my NeoVim configuration is on GitHub as well. It's in the .files repository. I'm going to also add a link in the description below. And with that, we now have a complete scanner for the entire log's lexical grammar. Fire up the REPL and type in some valid and invalid code. Does it produce the tokens you expect? Try to come up with some interesting edge cases and see if it handles them as it should. Challenges. The lexical grammars of Python and Haskell are not regular. What does that mean and why aren't they? I don't know Python or Haskell well enough, so I'm not sure. 2. Aside from separating tokens, distinguishing print-fu from print-fu, spaces aren't used for much in most languages. However, in a couple of dark corners, a space does affect how code is parsed in CoffeeScript, Ruby, and the C preprocessor. Where and what effect does it have in each of those languages? Dang. I'm pretty good at Ruby, but I'm not sure if I know anything about the C preprocessor. Yep, so I'm just going to read those, and if any of you is actually interested, then you could do it. 3. Our scanner here, like most, discards comments and white space since those are needed by the parser. Why might you want to write a scanner that does not discard those? What would it be useful for? I think comments could be used for documentation, like in the case of like magic comments in Go. 4. Add support to Lox's scanner for C-style block comments. Make sure to handle new lines in them. Consider allowing them to nest. Is adding support for nesting more work than you expected? Why? Okay, so C does not allow nested comments. I'm pretty sure I'm pretty sure it does not. Actually, what's this? Properties, open with document viewer set as default. So, what? I'm not sure what's happening here, but anyway, this is the C. This is not entirely relevant to the video, but this is the draft C language specification, and I think there is something about comments. Okay, we're not going to read all of this right now, but anyway, I'm pretty sure C does not support nesting comments. I'm going to commit, and we are going to implement C-style comments as a challenge. Okay. Let's see. So in here, okay, so if S matches this, S consume CPP consume line comment and break. If S matches as an asterisk, S consume multi-line comment and break, and then otherwise we add this token / token or okay, and I'm going to move these functions as to methods on the scanner. So it's going to be consume line comment and it's basically this, like so, and then func as scanner consume multi-line comment. So C equals S peak. Okay, I think we can put it in. Okay, yeah, we can pick inside of the switch like so, and case new line. What did we do with new line? We add the next. We change line, but we continue scanning. In the case of an asterisk, if s peak next equals slash, then it means we can finally end the comment, right? Yeah, we're going to do it in an infinite loop. And we do it until we reach the end of a file. So wait, so if we reach the end of the comment, I think what do we do? S current plus equals 2 and return. I think so. And then, and otherwise we report an error. I'm entirely not sure if this is what we are supposed to do, but hey. So in errors var unterminated comment, and this is going to say a multi-line comment met end of file error unterminated comment, like so. This is a syntax error, and let's see if we can actually get it working, like so. So in test, I'm going to write a comment test logs, and let's see, var test equals 2, and I am a multi-line comment, like so, equals 42. And let's see what log says about it. I think it's not happy. Did we advance? Did we forget to advance? will it work like this? Okay, yes, so it seems like it did correctly ignore the multi-line comment. Test equals 32. I am a single line comment, and we can start a multi-line identifier in here, and it should work correctly as well. So as we can see, this seems to be working correctly. So, and what would happen if we try to I am unterminated? Okay, yes, so now we get unterminated end of file. Okay, all of this seems just fine. Great. And let's just see if we are setting the indices correctly. So yep, so we are in here, we implement sCurrent by 2. We increment s.current by 2, and then this means that we are going to consume the asterisk and slash at the end. Okay, and this seems to be working fine. So I'm going to commit quickly. Okay. And back to the book. Design note, implicit semicolons. Programmers today are spoiled for choice in languages and have gotten picky about syntax. They want their language to look clean and modern. One bit of syntactic lichen. Lichen. And this is a very small gray or yellow plant-like organism or living thing that spreads over the surface of rocks, walls, and trees and does not have any flowers. Okay, so I'm pretty sure I've recently watched a video about lichens. Okay. One bit of syntactic lichen that almost every new language scrapes off, and some ancient ones like BASIC never had, is semicolon as an explicit statement terminator. Instead, they treat a new line as a statement terminator where it makes sense to do so. The where it makes sense part is the challenging bit. While most statements are on their own line, sometimes you need to spread a single statement across a couple of lines. Those intermingled new lines should not be treated as terminators. Most of the obvious cases where the new line should be ignored are easy to detect, but there are a handful of nasty ones. A return value on the next line, as in here, if condition return new line value. Is value the value being returned, or do we have a return statement with no value followed by an expression statement containing a string literal? So in JavaScript, at least, this would be treated as the end of a statement, but I think in C this would be considered the continuation of the return statement, but this is also because C does not have implicit semicolons. A parenthesized expression on the next line. Func parenthesize. Is this a call to func parenthesize or to expression statements? One for func and one for a parenthesized expression. I think in Ruby you're not allowed to put a space between the function identifier and the parentheses, so this would be a syntax error. I mean, it would be to expression statements. A minus on the next line. First minus second. Is this first minus second an infix subtraction or two expression statements? One for first and one to negate second. In all of these, either treating the new line as a separator or not would both produce valid code, but possibly not the code that the user wants. Across languages, there is an unsettling variety of rules used to decide which new lines are separators. Here are a couple. Lua completely ignores new lines, but carefully controls its grammar such that no separator between statements is needed at all in most cases. This is perfectly legit. Okay, let's see. I'm going to install Lua in the meantime. I think it works like this. Lua avoids the return problem by requiring okay, a equals 1, b equals 2. What's a? B. Very nice. Very nice. Lua avoids the return problem by requiring a return statement to be the very last statement in a block. If there is a value after return before the keyword end, it must be for the return. For the other two cases, we allow an explicit semicolon and expect users to use that. In practice, that almost never happens because there is no point in a parenthesized or unary negation expression statement. Go handles new lines in the scanner. If a new line appears following one of a handful of token types that are known to potentially end a statement, the new line is treated like a semicolon. Otherwise, it is ignored. The Go team provides a canonical code formatter, GoFMT, and the ecosystem is fervent about its use, which ensures that idiomatic styled code works well with this simple rule. So this is the reason why you have to add trailing. Why you need to add trailing commas at the end of a map, like this. This is because if there were no comma in here, the Go's scanning rules would place a semicolon in here, and this would be a syntax error. So I'm actually all for trailing commas. Python treats all new lines as significant unless an explicit backslash is used at the end of a line to continue it to the next line. However, new lines anywhere inside a pair of brackets are ignored. Idiomatic style strongly prefers the latter. Okay. This rule works well for Python because it is a highly statement-oriented language. In particular, Python's grammar ensures a statement never appears inside an expression. C does the same, but many other languages which have a lambda or function literal syntax do not. An example in JavaScript. Okay, yes. Here the console log expression contains a function literal, which in turn contains the statement. Python would need a different set of rules for implicitly joining lines if you could get back into a statement where new lines should become meaningful while still nested inside brackets. And now we know why Python's lambda allows only a single expression body. Oh yeah, I guess. Yeah, so this basically means that due to these, I mean, this was all explained here. I'm not entirely versed in Python, but I remember somebody once mentioned that Python tried implementing longer lambdas, but there was no way to express this in Python's formal grammar, so the proposal was abandoned. JavaScript's automatic semicolon insertion rule is the real odd one. Where other languages assume most new lines are meaningful and only a few should be ignored in multi-line statements. Multi or multi? Multi. Where other languages assume most new lines are meaningful and only a few should be ignored in multi-line statements, JS assumes the opposite. It treats all of your new lines as meaningless white space unless it encounters a parse error. If it does, it goes back and tries turning the previous new line into a semicolon to get something grammatically valid. This design note would turn into a design diatribe if I went into complete detail about how that even works, much less of all the various ways that a JavaScript solution is a bad idea. What's a diatribe?
Diatribe.
Against somebody something. A long and angry speech or piece of writing attacking and criticizing somebody or something. He launched a bitter diatribe against the younger generation. Origin from French, from Latin, from Greek. Okay. Much less all the various ways that JavaScript solution is a bad idea. It's a mess. JavaScript is the only language I know where many style guides demand explicit semicolon after every statement, even though the language theoretically lets you elide them. If you're designing a new language, you almost surely should avoid an explicit statement terminator. Programmers are creatures of fashion like other humans, and semicolons are as passé as all caps keywords. Just make sure you... I'm going to try to read it in an exaggerated tone. And semicolons are as passé as all caps keywords. Just make sure you pick a set of rules that makes sense for your language's particular grammars and idioms. And don't do what JavaScript did. Okay, this is the end of chapter 4. And I think we can read some of chapter 5, so that in the next video we can start implementing the code. And since we are in a new chapter, we can read it full screen. Chapter 5, representing code. Quote, to dwellers in a wood, almost every species of tree has its voice as well as its feature. Thomas Hardy, Under the Greenwood Tree. In the last chapter, we took the raw source code as a string and transformed it into a slightly higher level representation, a series of tokens. The parser we'll write in the next chapter takes those tokens and transforms them yet again into an even richer, more complex representation. Before we can produce that representation, we need to define it. That's the subject of this chapter. Along the way, we'll cover some theory around formal grammars, feel the difference between functional and object-oriented programming, go over a couple of design patterns, and do some metaprogramming. Side note, I was so worried about this being one of the most boring chapters in the book, but I kept stuffing more fun ideas into it until I ran out of room. Back to the text. Before we do all that, let's focus on the main goal, a representation for code. It should be simple for the parser to produce, and easy for the interpreter to consume. If you haven't written a parser or interpreter yet, those requirements aren't exactly illuminating. Maybe your intuition can help. What is your brain doing when you play the part of a human interpreter? How do you mentally evaluate an arithmetic expression like this? 1 plus 2 times 3 minus 4. Because you understand the order of operations, the old "please excuse my dear Aunt Sally." Okay. Parentheses, exponents, multiplication, division, addition, subtraction. So, you know that multiplication is evaluated before the addition or subtraction. One way to visualize that precedence is using a tree. Precedence, 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 precedence.
Precedence.
Precedence. Leaf nodes are numbers and interior nodes are operators with branches for each of their operands. In order to evaluate an arithmetic node, you need to know the numeric values of its subtrees, so we have to evaluate those first. That means working your way from the leaves up to the root, a post-order traversal. Starting with a full tree, evaluate the bottommost operation, 2 times 3. Now we can evaluate the plus, next the minus, and we get the final answer. So 2 times 3 is 6. Yes, this is 7, and 7 minus 4 equals 3. If I gave you an arithmetic expression, okay, there is a side note. And that's not to say a tree is the only possible representation of our code. In part 3, we'll generate bytecode, another representation that isn't as human-friendly, but is closer to the machine. If I gave you an arithmetic expression, you could draw one of these trees pretty easily. Given a tree, you can evaluate it without breaking a sweat. So it intuitively seems like a workable representation of our code is a tree that matches the grammatical structure, the operator nesting of the language. We need to get more precise about what that grammar is then. Like lexical grammars in the last chapter, there is a long ton of theory about syntactic grammars. We're going into that theory a little more than we did when scanning because it turns out to be a useful tool throughout much of the interpreter. We start by moving one level up the Chomsky hierarchy. The Chomsky hierarchy okay, well, I'm not familiar with that theory. 5.1 Context-free grammars. In the last chapter, the formalism we used for defining the lexical grammar, the rules for how characters get grouped into tokens, was called a regular language. That was fine for our scanner, which emits a flat sequence of tokens. But regular languages aren't powerful enough to handle expressions which can nest arbitrarily deeply. We need a bigger hammer, and that hammer is a context-free grammar. It's the next heaviest tool in the toolbox of formal grammars. A formal grammar takes a set of atomic pieces it calls its alphabet. Then it defines a usually finite, usually infinite set of strings that are in the grammar. Each string is a sequence of letters in the alphabet. I'm using all those quotes because the terms get a little confusing as you move from lexical to syntactic grammars. In our scanner's grammar, the alphabet consists of individual characters and the strings are v-valid lexemes, roughly words. In this syntactic grammar we're talking about now, we're at a different level of granularity. Now each letter in the alphabet is an entire token, and a string is a sequence of tokens, an entire expression. Oof. Maybe a table will help. Terminology. The alphabet is characters and tokens. This is lexical grammar. This is syntactic grammar. A string is a lexeme or token, and here a string is an expression. And the lexical grammar is implemented by the scanner, and the syntactic grammar is implemented by the parser. A formal grammar's job is to specify which strings are valid and which aren't. If we were defining a grammar for English sentences, eggs are tasty for breakfast would be in the grammar, but tasty breakfast for our eggs would probably not. I think I'm going to eat some eggs after I make this video. Rules for grammars 511. How do we write down a grammar that contains an infinite number of valid strings? We obviously can't list them all out. Instead, we create a finite set of rules. You can think of them as a game that you can play in one of two directions. If you start with the rules, you can use them to generate strings that are in the grammar. Strings created this way are called derivations because each is derived from the rules of the grammar. In each step of the game, you pick a rule and follow what it tells you to do. Most of the lingo around formal grammars comes from playing them in this direction. Rules are called productions because they produce strings in the grammar. Each production in a context-free grammar has a head, its name, and a body, which describes what it generates. In its pure form, the body is simply a list of symbols. Symbols come in two delectable flavors. Side note: restricting heads to a single symbol is a defining feature of context-free grammars. More powerful formalisms, like unrestricted grammars, allow a sequence of symbols in the head as well as in the body. Back to the text. A terminal is a letter from the grammar's alphabet. You can think of it like a literal value. In this syntactic grammar we're defining, the terminals are individual lexemes. Tokens coming from the scanner like if or 1234. These are called terminals in the sense of an endpoint because they don't lead to any further moves in the game. You simply produce that one symbol. A non-terminal is a named reference to another rule in the grammar. It means play that rule and insert whatever it produces here. In this way the grammar composes. There is one last refinement. You may have multiple rules with the same name. When you reach a non-terminal with that name, you are allowed to pick any of the rules for it, whichever floats your boat. To make this concrete, we need a way to write down these production rules. People have been trying to crystallize grammar all the way back to Panini's Ashtadhyayi, which codified Sanskrit grammar a mere couple thousand years ago. Not much progress happened until John Bacchus and company needed a notation for specifying algo 58 and came up with Bacchus-Naur form. Since then, nearly everyone uses some form of BNF, tweaked to their own tastes. Side note: yes, we need to define a syntax to use for the rules that define our syntax. Should we specify that meta syntax too? What notation do we use for it? It's languages all the way down. Back to the text. I try to come up with something clean. Each rule is a name, followed by an arrow, 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 arrow.
Arrow.
Arrow, arrow,
Arrow.
arrow. Followed by an arrow, arrow, arrow. Followed by a sequence of symbols, and finally ending with a semicolon. Terminals are quoted strings and non-terminals are lowercase words. Using that, here is a grammar for breakfast menus. Side note, yes, I really am going to be using breakfast examples throughout this entire book. Sorry. Breakfast, arrow, arrow, protein with breakfast on the side. Breakfast is protein, breakfast is bread. Protein, crispiness, crispy bacon, protein sausage, protein cooked eggs. Crispiness, really, really crispiness. Okay, so this means that we can get like really crispy bacon or really, 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 really crispy bacon, because I think this can be repeated ad infinitum. And cooked means you can get scrambled, poached, or fried eggs. How do you poach an egg? Okay. Oh wow. Outside the shell by poaching. Wow, this looks so nice. Anyway. Bread is toast, biscuits are an English muffin. However, I live in Asia, so there is no bread for me. Okay. We can use this grammar to generate random breakfasts. Let's play around and see how it works. By age-old convention, the game starts with the first rule in the grammar, here breakfast. There are 3 productions for that, and we randomly pick the first one. Our resulting strings looks like protein with breakfast on the side. We need to expand that first non-terminal, protein, so we pick a production for that. Let's pick protein, arrow, cooked eggs. Now we need a production for cooked, and so we pick poached. That's a terminal, so we add that. Now our strings looks like this. Poached eggs with breakfast on the side. The next non-terminal is breakfast again. The first breakfast production we chose recursively refers back to the breakfast rule. Recursion in the grammar is a good sign that the language being defined is context-free instead of regular. In particular, recursion where the recursive non-terminal has productions on both sides implies that the language is not regular. Side note. Imagine that we've recursively expanded the breakfast rule here several times, like bacon with bacon with bacon. In order to complete the string correctly, we need to add an equal number of on the side bits to the end. Tracking the number of required trailing parts is beyond the capabilities of a regular grammar. Regular grammars can express repetition, but they can't keep count of how many repetitions there are, which is necessary to ensure that the string has the same number of with and on the side parts. Back to the text. We could keep picking the first production for breakfast over and over again, yielding all manner of breakfasts like bacon with sausage or scrambled eggs with bacon. We won't though. This time we'll pick bread. There are 3 rules for that, each of which contains only a terminal. We'll pick English muffin. And what's an English muffin? Okay, so it's basically like a bread roll. Oh wow. Oh wow. This looks nice. With that, every non-terminal in the string has been expanded until it finally contains only terminals, and we're left with breakfast, which is poached eggs with English muffin on the side. Throw in some ham and Hollandaise, and you've got eggs Benedict. And okay. And Hollandaise sauce is egg yolks, lemon juice, unsalted butter, and salt and ground white pepper to taste. Nice. So that's basically like eggs with butter. Nice. I'm going to have to try and make it at some point. Anytime we hit a rule that has had multiple productions, we just picked one arbitrarily. It is this flexibility that allows a short number of grammar rules to encode a combinatorially larger set of strings. The fact that a rule can refer to itself, directly or indirectly, kicks it up even more, letting us pack an infinite number of strings into a finite grammar. 512, enhancing our notation. Stuffing an infinite set of strings in a handful of rules is pretty fantastic, but let's take it further. Okay, this is a long section, so I think we'll call it a day. The name is Karol Moros, and you have been watching Make Programming Fun Again.